Okay. Okay. So thank you for bearing with me. First of all, good morning, Brandon, and thank you for the help. Good morning, Xavier. Thank you for the patience. Good morning, Stephanie. Good morning, Charlene. Good morning, Judith. Good morning, Emily. Good morning, Ethan. Good morning, Ariana. Good morning, Alexis. Good morning, Maria. Good morning, Shaynell. Well, wow. Scooby-Doo. Okay. Wait, and now the chats. I'm just trying to get normalized here. Good morning, direct chat person who's helping me with the microphone stuff. Good morning, direct chat person with the double. Good morning 2.0. That is hilarious. Okay. Good morning 2.0, direct chat person. Good morning, Ethan. Good morning, Ryan. Good morning, Stephanie. Okay. I think that's, oh, well, okay. 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 Um, so here is the deal. Uh, And good morning, Stephanie, if I didn't say, sorry. So that's not the way I wanted to start today, of course. I want to say that all of you who are in the room right now, for the most part, you deserve better than that. No, I mean, what you deserve I want to offer you my congratulations and my thanks. Really, we're gonna move on in the physics course in a moment. Like really move on, like to totally new material and to new material to potentially a fresh start for some of you in terms of the lecture, expectations and material and all that. But a beat first to say, like, you just did a big exam. I mean, it may have been shorter than some of you were expecting. I mean, I know I only asked you in the end to do two out of the problems after you hopefully studied more than two of the problems. Hopefully, maybe for some of you, that was a bit of a relief. I don't know. But no matter what, that was a real undertaking, in my opinion. If you tried to do that exam legitimately, it, it was an undertaking. Uh, uh, if it was at all fun in any way for any of you, then that's terrific, and I'm glad. But I don't think it was probably 100% fun. Um, and we will go on in a minute, like uh, because I have not looked. I have not. I haven't. I mean, they just came in, obviously, for the most part. So I'm not making any comment on the specifics of what you did in your solutions to the problems. But I've come to believe that it's important for me to pause before I even look at them. I think it's important for you to know that I think you just accomplished something by doing the exams, by turning them in on time, which for some of you may have taken a lot of effort, and then showing up to this class on time, even though then I was a mess. Um, and I think that's effort. I think that is responsible. I think it's an accomplishment. And frankly, in my life as a physics student and as other kinds of students and everything, once I was done with an exam, I was usually exhausted, and sort of proud of myself, but sort of like really scared of what the outcome on the exam was. Like often I was. Um, and I wish that there had been more of a concrete moment sometimes where I could just feel accomplished by doing the exam and feel proud of myself and feel relieved before moving to the next stage of like, what grade did I get? Or am I doing okay in the course? Or all that kind of stuff. So I don't want to take the whole period on this, obviously, but I do just want to say each and every one of you who turned in an exam on time and got to this class on time, only to find that I was a total mess, you did something impressive, regardless of whatever the next stage is of whatever your grade is on the exam. And by the way, I also expect, well, I'll get to that in a minute, but regardless of what your grade is on the exam, and it's going to take me a little while to get that back to you. I want you to right now feel relieved and proud of the fact that you did something right and possibly something hard in many cases. And I mean that. I'm going to be slightly more specific now. If you turned in an exam at 1050 that you're like really proud of, like you actually think you rocked it, you think it was easier than you thought it was going to be, or like whatever, then great. Then I'm proud of you too. And probably you probably did do well, and you probably are doing well in the course, and that's all terrific. And then I'll see you in the next course in 204. If you, on the other hand, are one of the people that actually deep inside are feeling a little shaky about what you just turned in, if you're feeling like, oh, like I don't really want him to see it, or like I don't want to see it again, or like, oh, that was not what I want. If you, and I've been in both of those situations, I assure you, I've been in both of those situations. If you're the person right now who's feeling like, oh, and I wish he wouldn't even talk about it, I just want to move on, then I won't, and I will move on. But I want you to know too, having been that person who has turned in something that I did actually internally did not feel that great about, or felt like this just shows I don't know what's going on in this class or whatever. If you are that person, then the fact that you were able to cut off your work and stop doing what you were doing and get it in on time and not let the perfect be the enemy of the good, if you know what I mean. Like if you were able to just be like, well, this is what it is. And now I it's not going to be great, but I just have to get it to him and I just to get to class like he said. That can be very hard for many of us to just do that, to right, to not be perfect and just to like get. And so if you're that person, I'm telling you, I'm proud of you too. Like I know it's an accomplishment, and we may find out that maybe your grade on this exam is like not what you want it to be. Like I can't promise. I don't know. That's why I'm giving this speech now. I literally don't know what's in those documents, but I know that you each accomplished something by turning it into me, no matter where you are in your feeling of the document. And probably I'm also warning you when you get them back, which is going to take a little longer than any of us would like, because I am a little overwhelmed and I have a lot of them, and I apologize in advance. It's going to take a little longer than any of us would want it to take, but you will get them back, and you'll get them back in time to know what to do for the final and all that kind of stuff. But when you get them back, even if for some of you the grade is not what you're used to or what you want or what you think of yourself, I'm also warning you in advance that's not whatever grade you get on this document is not your final grade for the course. And it's also not your evaluation in life and all that kind of stuff. There's still room to do well in this course. So all I can't. I literally can't say anymore because I don't know, right? And it's going to take me a while before I know. You're going to have to bear with me. We're going to move on in the course now to a totally different thing. For some of you, you can consider this a fresh start, and you could still turn in homeworks and you could still turn in old homeworks. And if you're now nervous about where you are in the class, do a lot of the game participation things. Like there's definitely still, it's like a checkpoint in a video game. I mean, it is a checkpoint. There is still time to do okay or to do great. Okay. So I'm going to move on, and it'll be a little while before you know exactly what you did on that exam, but you should take this period of time before you know what you did or what I think you did on the exam. You should be psyched and you should recalibrate and like use this as an opportunity to be like, we're a class again now, and we're like fresh starting. Okay. Okay. Sorry. Oh, okay. I'm looking at the chat. So I'm going to move on, but I'm looking in the chat. Oh, 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 okay, okay, okay. Wait, sorry. So I'm seeing good things in the direct chat. Give me 1 second. I mean, there's something I have to respond to. Okay. 1 second. 1 second. Sorry. Okay. So um I'm looking in the direct chat. I appreciate that you're hearing me and people are saying like things that are is not private, but like one person is admitting in the direct chat that one of the questions was making them doubt like a lot. And then someone else is saying thank you for the encouragement. So I appreciate. So thank you for the thank you. And those of you in the direct chat like should oh yeah, no, okay. And one of you is being hilarious as usual. Okay. I mean it. I mean, no, and also I hope they get to know you all better. You know, this is like our first exam together, right? I mean, it is a little, and I do have children, who go through school or and struggle in school. Um, it's our first exam together. We have another one, at the end of the course, and again, let me be clear about this logistically. You have to be, I mean, I ask you to be patient with me about getting these back. One of the reasons I made them shorter is to try to like not get into a jam of, I mean, it's partly literally so I can get them back with more feedback and more efficiently. It won't be as efficient as it should, but you will get them back in time to get enough feedback to know what to do with the final. Like that's what I consider like the ultimate like issue, right? What am I saying? Why am I saying this? But we're good. But I'm hoping part of why I make this whole speech now. I'm not going to make this speech every time, but I'm hoping to be with you guys for a while, right? Like this is we have another class together. I hope and there's two exams there, and it's all very similar. Part of this, like, is getting used to like how I do, getting used to the expectations and stuff. And once you sort of get used to them, it's the same routine in physics 204, like for what it's worth. So, okay. No, so I'm glad if this, but I mean every word of what I'm saying. It's going to work out for most of you better than you think or better than you feel. The way you feel about the course and yourself in physics is always at the height of worseness, like in the middle of an exam. Like that's like the way I feel like it's at the height of when I'm grading the exam. Like that's always the worst moment. So yeah, I just want to remind you, it's pretty my experience is that each one of you is probably going to do better in the course than you're feeling about it right now. If you stay with the program with me, like if any of these words mean anything to you and you just hang in there, you will probably do better than you might be feeling right now. And again, and also if you're feeling good, I don't want to ruin that either. I mean, yeah, okay, but no, I mean it, and yeah, I mean it. Okay. Huh, what? Oh, wow. Well, now I'm actually hearing some really nice. Ha, ha, okay. Okay. Sorry. Okay. Um, wait. Okay. So the chat is over. And if you're trying to keep me from doing more physics, you're succeeding. Hold on. No, oh, thank you. And I'm seeing the public chat. Okay. No, oh, no. And I appreciate if someone's also indicating the thing, if the videos and stuff like that are helping at all with any of this, that's great. That I'm really glad to hear that. I mean, I'm glad to hear all of this, but whatever. Okay. Uh, don't expose. Ha, ha, ha. Okay. Yeah. Um, uh, right. Delaying the physics lesson. Right. Okay. We're gonna go back to yeah. Um, I mean, it's hard for me to, even if you are literally just doing this to keep me from teaching, I will get, but it's hard for me to, if nothing else, and look, at some point, like each of you, I hope over the next 2 semesters, like at some point visits me in the office or whatever, and I'm going to have a lot more time in the office next semester too, for what it's worth, when maybe some of you will need it or want it even more in Physics 204. I'm rearranging the schedule to have more time in the office for all this kind of stuff. Um, and just, I guess you know what the biggest message is? Anytime I give these like speeches or encouragement, I really do mean them. I really do. And there's 1,000 reasons. Like I'm not in it. I'm not doing this whatever. It's sincere, and part of the sincerity is I really love physics. And I love teaching physics. I hope that's clear. But part of the love of it and part of what I want to get across to you guys is it wasn't easy for me either. And it's not easy. I don't want, I want you to know that I know the struggle. The struggle is real. Like, For real. And you know what? It is not a struggle against equations. Everybody thinks it's going to be. And then most people find out that equations are not the issue. You guys are so over prepared for equation. Like you know how to do science if you're here already. The struggle is always against our weaker selves. It's always the struggle is internal. And believe me, I know the struggle. And I just that's and I'm here to help with that struggle because I'm not going to deny I have had that struggle and I have won. I've lost the struggle enough times to know, and I've won the struggle enough to have things to say about it. But believe me, I don't do physics because it came easy or because it's just like a joke. I do it because I love the hardness of it. Anyway, all right. So physics, right? I've heard of it. Have you heard of it? So we totally move on. Oh, wait. Oh, cool, good. I'm glad. No, thank you. What you're saying in the chat, I see it, and no, I do, yes, thank you. I'm not going to fall into the route, but no, I do mean it. And come visit me, and we'll talk more, even specifically about it. All right. So what we're going to get to now is more GPRs. One thing to realize in this class is it's all about Galileo principle of relativity. Believe it or not, every new thing we learn, even including physics 204, is some disguised or weird new version of that the laws of physics are the same in all inertial reference frames, that the laws of physics are the same at all constant velocity. And I'm serious. It doesn't matter if you go into in fact, particularly if you get into Einstein in 1905 or 1950, or you get into contemporary physics like late 20th century, it's still all a big expansion of all the implications of how we could stand on an Earth that we believe is moving at 65,000 miles an hour all the time and yet not feel it at all. Like all of physics really is an investigation of the crazy implications that come out of that idea, right? So we're going to have two more versions of Galileo's principle today, but you'll have heard of these implications phrased a different way. Where we're getting into now, as you might guess from Lab 5 and all of that, is Newton and Newton's laws. So what I'm going to do now, so we're okay, so it's like a new topic, right? It's all connected, but it's a new topic. It's a topic you've totally heard of in high school, maybe middle school. Most of what I'm going to say today, especially also because I know some of your brains are fried, much of what I'm going to say today is stuff that I think you've heard before, like Newton's laws. We're going to do Newton's three laws of motion today, okay? So in some ways you could chill a little bit. I'm going to be giving you information that you, I think, already have somewhere in your brain, but I want to give it to you I want you to see it in a slightly new way and see how we apply it in more advanced physics contexts. Okay. So try to view it this way. So first of all, um, okay, in the same year, 1642, and early in 1642, Galileo, my hero, our hero, dies. I mean, like in Italy, under house arrest. And then later in that same year, some people say Christmas of that year. Then there's some debate. It might have actually been a little bit later, might have actually been January. There's still some, but basically, at the end of that year or the beginning of the very next year, Newton is born in England. So that's mystically convenient. Um, um, and Newton, as you know, uh, makes a major contribution to the entire study and development of physics. Among other things, he writes this huge book and publishes this huge book called the Principia Mathematica. To this day, one of the most important texts in the history of science, maybe one of the most important, it's certainly in the top 100 texts of historical importance in general. And here in the Principia Mathematica, he does a number of things. Number one, from one side of his brain, as you know, he develops the fundamentals and the notation for differential calculus, right? I mean, you know this. I mean, I'm not saying he's the only one in the world. There's also this guy Leibniz in Germany, and Lord knows there's probably tons of other men and women privately developing calculus in other countries in different notations and all of that. But he is one of certainly the front runners of people who develops the idea of differential calculus. And he partly does it so that in the other side of his brain, he can expand on Galileo's work and lay down some laws of physics, right? Which is what we're about to get into right now. And remember, Galileo did all this work, this groundbreaking work, the scientific method, the acceleration due to gravity, like the 9.8 number. Kinematics equations, like much of what we've been studying thus far, is like all Galileo, and specifically Galileo's principle of relativity and all the stuff. But remember, kind of the funny thing about Galileo is the main principle says the laws of physics are the same in all constant velocities. Galileo doesn't literally lay out what those laws are. I mean, there's just no explicit place where he says, this is the way nature must work. This is the way nature. He says, whatever the laws are going to be, are going to work a certain way. So then Newton comes along and definitively lays out a number of laws. It says, this is the way nature works, right? And three of them you know as the laws of motion. Okay, and so we're going to go through them now in the lens of this class. I mean, we're going to need them for the rest of the class, but also I want to establish what they mean through the lens that we've established, that we've already set forth in this class. So I'm just looking. Oh, yeah. Wait, sorry. Oh, I'm looking at the chat. Oh my God, that would be awesome. Sorry, I'm distracted. So someone, that's right. It's you already see the class. Okay. I don't want to distract myself right now, but I'm glad that you're already aware of when Physics 204 is meeting next semester. And I think you'll notice, wait. Well, okay, I can't get into that now. We're making it more. Okay. I'm getting distracted. I very much hope to see you guys in Physics 204. And yes, if I could see you in person, as you know, I do teach certain in-person sections of that class, and we're expanding that. Although I guess it's 2 semesters from now. Not anyway. I hope to see you in person, and I don't teach over the summer. I'm sorry. Well, as of right now, I don't. I mean, as of right now, I don't, and I think that's a fair assumption that I won't this summer. Sorry. Wait. Okay, you're very kind. Okay, and you're totally. I know you're doing it just to keep me from. Newton is not that boring. You can handle Newton. But wait, but there. No, okay. Oh, wow. Okay. No, but again, anything talk. Your futures are important to me. I mean, they are, including your next semester. So again, like if any of this, if I can help with any of these things, or registration or advisement, whatever, like either come see me in my office on Tuesday or like reach out and we'll make a Zoom or a text or I'm serious. I'm just also worried that I like lost 10 minutes to technical. So we're going to go back to Newton. But yes, I mean, there is this weird thing that Galileo dies and in the same year Newton is born. Like people do get very mystical about that. And then there's some third level to it that I always forget, but you can look it up. There's some third way in which then Einstein's birthday somehow connects that. I mean, obviously, I can get very mystical about these things. I think that's probably coincidental, but there's some funny way that you can connect the souls of Galileo, Newton, and Einstein. That's like sort of gratifying to think about. But okay, what I'm going to try to do here, it's 11:26. My goal for today is just to lay out the 3 laws, not get too analytical about each of the 3 laws, but lay them out so that you can see how they work in the backdrop of Galileo and what we have to do in the future of this class. So again, knowing that you've, I think, heard of these before, but now try to take them into a new perspective. Here's Newton's first law of motion in the way that I would ask. Here's my words for it. Now, any words we use are a translation. It's not like Newton did not, even though he did live in England, he did not write this book in English. He wrote it in Latin. So anything we do is like a translation anyway, but some translations are better than others. So here's how I would put it. Okay. So wait, wait. Can I sneak people who won't be in your? Yeah. Wait, I'm always open for guests. I'm not sure if this is a joke, but I always welcome guests if for sure for real. And then yeah, nothing is coincidence. I do also agree with that, but we don't get me started. But okay. Um, 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 um. So here's the first law. The way I say it. Now, again, it's not like each exact word. I mean, some of the words you could play with, but not a lot of them. And what I want you to see is the structure of at least the way I understand this law. The way, so what my handwriting says is unless acted on by a net external force, an object at rest stays at rest, and an object in motion stays in oh, that's illegible. And an object in motion stays in motion at constant speed and in constant direction. Or you could say at constant speed and in a straight line, like same thing. So just notice. Now, again, you've heard this before. I mean, I believe you've heard this before, but notice a couple of things. First of all, it was really three parts to this law. The first part is like a condition or a, wait, I'm just questioning whether I should write all this down now, but the first part is a condition. It's saying here's where and when the law is going to operate. It says unless acted on by a net external force, and the acted on is referring to whatever object we're about to be talking about. So it's first of all saying this law is what applies when when a object is not acted on by a net external force. Any object that's acted on by a net external force is not what we're talking about here, right? Okay. Now, we may not know exactly what we mean by net external force yet. Like, no one's defined the word force, but external means from the outside, and net means what you have left over after you've added everything up and you've taken into account minus signs. Right, like one example from real life is, if you look at a bag of potato chips or whatever, and it says net weight 3 ounces, like what they mean is if they weighed the whole bag of potato chips and then they subtracted um, the weight of the bag, then what's left over is the weight of the potato chips, and that's what you care about, and that's what they mean by net weight, right? So, or same thing with like, there's other examples of that. So net means like the sum of all the forces, taking into account minus signs. External means from the outside, and force, well, in short, means a push or a pull, but we'll get into that in a minute. Um, yeah, I guess I do want to write this down. Hold on a second. Okay, so first of all, the condition. Oh, I see. But yeah, yes. Okay, I get the guess thing now. Yes, yes. That's yes. Um, the condition is saying when it says unless acted on by a net external force, what we're really saying there in English, and this is what I want to emphasize, really saying is unless affected by another object. That's what that really means. When it says unless acted on by a net external force, it means unless the object is interacting with another object. So, what this condition is really telling us is that the first law, whatever the first law says, is about to be a description of what we would expect to happen, what the base case or natural state of a object's motion would be if no other objects were messing with it. Okay, I mean, this is a base case. This is the expectation case for an isolated single object. That, okay? Um, whoa, sorry. Okay. So the claim, the Newton's first law, first is saying we're only dealing with an object in isolation. Then it's saying of an object in isolation, now we're going to split into two cases. Either we're talking about an object that you just notice right at this moment at t equals zero, that you notice it has an instantaneous velocity of zero. That's one case. Or we're talking about an object that you notice right away, it has an instantaneous velocity of not zero. And of course, logically, that covers everything, right? Like either it is zero or it isn't zero. Um, so what Newton says is it's that in either of these two cases, the prediction is the same. If you walk in and catch an object not doing anything, what you can expect, like not moving at all, you can ex- you can expect. Oh, and sorry, and we're talking about an object that's isolated from other objects now, and I don't mean totally unrealistically, it could be a puck on an air hockey table. Like that's reality, right? But I mean, a puck on an air hockey table. I don't mean isolated, like socially canceled. And I don't mean isolated, like there is no universe. I just mean an object that's basically not touching any other object, right? So, like a puck on a bed of air on an air hockey table would be such an example, or like a meteor in outer space, a little bit harder to access, a little bit harder to imagine, but like, right? Or or a puck on ice, right? Which Newton certainly would have access to, right? So I'm talking about an object that is not like rubbing against some object or anything like that, or being pushed or pulled in some way by some other object, including a floor. So Newton says, once you're picturing that kind of object, again, I think the easiest example is like a puck on ice or a puck on an air hockey table. Once you're talking about an object like that, um, there's two possibilities. You either walk in on it while it's sitting around, or you walk in on it, start your stopwatch while it's not sitting around. And what Newton says is in either of those cases, what you're going to find is that the object maintains constant velocity. If it has zero, it's going to maintain zero. If it has something else, it's going to maintain the something else, right? So now, again, you've heard this before. Again, well, you've heard this before, but but let's look at it this way for a moment. It's a condition, and then it's two cases. But then in the two cases, he's saying the result is the same. So, like, why are we even bothering to split it into two cases if the result is the same? Like, the result that we're claiming here is that objects, when they're left alone, maintain constant velocity. Like, that's what we're saying. That's what he's saying. Well, the reason we're dividing it into two cases, I mean, there's many reasons perhaps, but one big reason in my judgment is that one of the two cases is is almost obvious. Well, one of the two cases most people would and did agree with. I mean, most normal people that don't care about physics and most people that had written about anything resembling physics to that point, such as Aristotle, would agree with the first part. I think you would, right? If you walk in on an object not doing anything, your expectation is that the object will continue to not do anything, right? An object that's sitting still tends to keep sitting still unless you make it do something else. That's the part that seems reasonable to most people. It's the second part that's a little counterintuitive. Like, for example, Aristotle certainly didn't think. I mean, he wrote the opposite. He believed that objects naturally slow down, which is what most of us, especially if we're not studying physics, tend to think that. Sorry. Most of us tend to think that objects left to their own devices would tend to slow down, which is why we worry about, do we have enough gas for our car, or we think we have to keep pushing the ball to keep the ball going in a soccer game or whatever. But and like I said, even like very advanced thinkers in and writers of natural philosophy tended to write down laws that suggested things left to their own devices will slow down. But what, as I'm sure you've heard in middle school or high school or whatever, is that Newton saying, yeah, but no, like you think that your general experience tends to suggest that we need to help objects in order to move, but that's not really right. That's because we're tending to look at objects that are interacting with other objects. Like, yes, once a ground exerts a force called friction onto an object, then the ground will tend to slow down the object. And so we need, like the tire or whatever. So we need to help the tire along if it's being forced to slow down by something like a rough ground. But really, that gets into the next laws. We need other laws to deal with that. If we want to know, we need laws that tell us exactly how influences from other objects do lead to decelerations and things like this. But what Newton's, I think, very scientifically doing is saying, but the only way you can analyze what forces, what interactions with other objects do is if you first know what would happen if they weren't doing that. Like, we need a control in the mental experiment, in effect. So Newton's first saying, hang on. First, if an object is by itself, what do we expect it to do? Before we introduce other forces, what is the natural state of motion of an object? And Newton didn't have air hockey tables, and Newton didn't have access. I mean, he had access to astronomical data, but he wasn't exactly going to the moon and throwing things around, like where there's no atmosphere and stuff, no air friction. Um, but Newton had the work of Galileo. And what Galileo was smart enough to have done, and Newton had calculus, between the two of them, the basic thinking is, look, I may not have a perfectly smooth ice skating pond. I may not have perfect access to perfect outer space. But what I can easily do, now this is Galileo. Now, what Galileo did that's so smart is he could take like a ramp and put things at the top of the ramp and let things go down the ramp. And first have it be sort of a rough ramp, or it doesn't even have to be a ramp. I mean, ramp, it doesn't even have to be tilted. I mean, it was often tilted, but it could also be even horizontal. He could flick something on a horizontal surface that was first pretty rough and watch as the object like slow down and eventually stop, right? Then he could smooth the ramp a little bit, make it a little less rough, like make it a little bit less friction, and observe and measure as the object takes a longer time to slow down and stop, right? Goes a farther distance before it stops. Then he could smooth it a little bit more, observe again, smooth it more, observe again, and do what's called successive approximations. In other words, in the physical world, Galileo could study what's happening when we have less and less and less friction, make a graph out of it if you like, right? See the trend of, oh, less friction means less slowdown, means longer period of time that you stay in a straight line at basically a closer and closer to a constant velocity. And he could take that concept to the limit in the physical world. That's called successive approximations, right? In physics, I mean, in the physical world, it's called successive, not successful, but successive, like one after another, successive approximations. And what that translates to in math is taking something to the limit, like as the friction force goes to zero. The limit as the friction force goes to zero of 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 the acceleration, let's say, equals zero. Do you see what I'm saying? Right? So so they could see the trend that as you're making less and less friction, you're making less and less slowdown. So it's friction that's responsible for the slowdown. And they could go to the limit in their minds, whether you want to think about it physically or mathematically. If you go to the limit in your minds, the strong suggestion is that no friction or no interaction with another object would mean no slowdown, right? So, first of all, what I'm trying to say, and I am watching the clock, on this first law, the first law is trying to say both of the cases, the obvious case of no initial motion and the less obvious, more surprising case of lots of initial motion, both lead to the same conclusion, which is if you leave an object alone, it ain't going to change the way it's moving. It's not, it has no reason to change its velocity, i.e., it has no reason to accelerate positively or negatively if it's not interacting with another object. That's the claim here. Now, before I even go on to the other laws, right? So I'm saying part of why you could believe this is just, and maybe this is the way it was explained in high school or middle school or whatever. Part of why, so we're trying, so Newton's trying to say, in dividing into two cases, he's really trying to say, from here on in, I want you all to understand. If you understood the first case, I want you to understand the second case and realize they're both part of the same thing. The claim is that the second case is just like the first case. No matter what, objects left alone want to maintain constant velocity, right? But even if you don't believe anything I just said about success, or you're not comfortable like with anything I just said, I want you to also see it this way. Really, what this is. Um, Like I'm sort of trying to convince you of something that is counterintuitive. Again, like if you're at all thinking like, no, objects left, if you're thinking this is Smurf Village, which is the way I thought about it when I first, if you're thinking like, all right, yeah, I mean, I guess like in a perfect world, in an ideal world, if you left an air hockey, if you left a puck on a perfect air hockey table, like, and you hit it, like, I guess it would just keep going in a straight line and not slow down. Yeah. But even air hockey tables aren't perfect. And like, eventually it's going to hit the side anyway. So this is like kind of pie in the sky, no pun intended. This is kind of just like one of these idealizations that's sort of more about the world of math in my mind than really about the real world of science. You could think that. And that's kind of what I did think. But if you think that enough, you might ask, but why would Newton even like try to convince us of this? It's like, I could sort of buy what he's saying, but I have to try so hard to buy what he's saying. And if it's turning up over like 2,000 years of historical writings on this, like why bother? That's a fair thing to wonder. What I want to say is there is a motivation, there's a reason that Newton's trying to show us why the two cases are the same. And the reason is Galileo's principle of relativity. This is what I would argue is form 6 of Galileo's principle of relativity. And it's not a coincidence. Like Newton was aware of Galileo's work, and it's also not plagiarism, like at all. I mean, it's like totally different words for it and everything. But what Newton's really saying is, dudes, there's nothing special about velocity zero. And that's really what I'm getting from Galileo. Galileo is saying zero velocity is not like the Earth. The Earth is zero velocity from the frame of reference of a person standing on Earth, but the Earth is not zero from the frame of reference of the sun. Like zero is in the eye of the beholder. Zero is not some special like there is no thing in the universe that is objectively sitting still. Sitting still is what anything can be doing as long as you, the observer, are sitting still relative to it. Right? That's what Galileo is telling us, is that zero is not a special state. So what Newton's saying is, oh, right, zero is not a special state of velocity. Whatever we observe about a zero velocity object must be true about any velocity object because velocity is just a matter of what perspective we're in. Bottom line, and I will move on. Bottom line, if you think it's ridiculous, if you're looking at like a soda can on your desk right now, a coffee cup on your desk, and you know in your gut you do not expect that coffee cup to just spontaneously start moving, like that would be absurd, right? We know if it's sitting still, unless you do something to it, it's going to keep sitting still, right? That's absurd. So now just back up and imagine, well, if the coffee cup was moving, but you were moving alongside of it, watching it, like if the coffee cup is moving and you're moving, or as you are on planet Earth, right? Like the coffee cup is still relative to you, but you are on an Earth, or say we were doing it on a subway. Say you had a coffee cup next to you on the subway, right? You don't, a good sub, like a train, like a smooth subway, right? Or an airplane. You're sitting on an airplane, a smooth cruising airplane with a coffee cup on your tray table. Unless the airplane does something weird, like hits turbulence or like lands or turns, you don't expect your coffee cup to just spontaneously do anything. You expect it to stay still relative to you. But that means it's totally moving relative to Earth. I got it 500 miles an hour, right? So your expectation that it doesn't start moving really means that someone else watching from Earth is expecting that the coffee cup shouldn't spontaneously slow down or speed up or do anything. They're not expecting that it stays still. They're expecting that it stays at 500 miles an hour. Right, because they're in a different perspective. And velocity is just a matter of perspective, according to So really what Newton's first law is saying is, look, if you really get this Galileo deal, if you're really comfortable standing on an Earth and believing that the Earth is going 65,000 miles an hour, then you're getting that there's nothing special about the zero velocity case. Therefore, whatever we ever believed about the zero velocity case, we got to believe about all velocity cases. Therefore, what Galileo is saying is from now on, I'm sorry, what Newton is saying is velocity is a relation between two objects, not a property of one object. So if you've got one object by itself, whatever it's doing velocity wise, you should expect that it'll continue doing that. That it's Galileo form number 6 is Newton's first law. Okay. Um, so that's law 1. I'm looking at the time. We have 12 minutes. Law number 2, I'm going to say quickly because we're going to spend like the rest of the semester and the rest of our lives like dealing with it. So law number 1 is what happens if there's no net external force acting on an object. If there's no net external force happening on acting on an object, i.e., if there's no other objects interacting with it, we expect it to not accelerate. That's law number 1. Well, then law number 2 is, well, okay, now can we get down to business here? Fine, that's the base case. But what happens to an object if it is subjected to a net external force? What happens to an object if some other object is interacting with it? And the answer is it accelerates in exactly this fashion. I'm just looking at my colors. Yeah. It is simply this. Okay, this is the second law. It is so simple, but so powerful, or so simple and so powerful, and so mathematical that I'm not kidding when I say, in a sense, the rest of the course, and in a sense, the rest of physics, other than Einstein, is like all about this. So I'm going to try to, and obviously you've already started doing at least one lab about it. Like you already have a whole sense of it. So I'm going to hold my tongue on this for a moment. Like we're going to, get deep into this next class. Um, I'll just break down I'm just going to translate it for the moment. Um, um, F net equals ma. I mean, I say either sum of the forces equals ma, or you could say F net equals ma. But the important thing to realize is it's not F equals ma. It's the sum of all of the forces equals ma. M means mass measured in kilograms. We'll get into that in a minute. I mean, you know that, but we'll get into that. acceleration means, I mean, A means acceleration, and that means everything that we've just been studying for like a month and a half. The second derivative of position with respect to time, instantaneous acceleration. And acceleration is a vector, it has magnitude and direction. So, in a sense, everything we've been studying is the definitions and observations of and the knowledge we need to put together for what it means for an object to instantaneously accelerate. In other words, for a month and a half now, and in sort of in the spirit of Galileo, we've been studying the effect known as acceleration and how powerful an effect that is. Now, what Newton's doing is backing up and giving us like the cause for that effect. And he's saying what causes acceleration is a bunch of forces acting on an object. And given a bunch of forces, the heavier the object is, the less it will accelerate. Like heaviness, mass is resistance to changes in motion. And the lighter an object is, the more it will respond to forces by accelerating. So if you don't force an object, it won't accelerate. That's Galileo. If you do force an object, then the more you force it, the more it will accelerate given a certain amount of mass that it has. Okay, like that's the summary of this. And again, I think you, in big picture, I think you know that. The issue, though, is with 7 minutes left, the issue is what exactly do we mean by a force, right? What exactly do we mean by a force? Well, I think the easiest way to see, oddly, okay, um, what the easiest way to see what a force is to look at the third law. Interestingly, so let's do that. Now, the third law. So, what I want to argue with 6 minutes left, I want to argue that in a way, the third law is the third law. I mean, they're in order for a reason, but I think that that the third law is really, in a way, the definition of force, or it certainly is. It's a statement that allows us most easily to picture what Newton means by force in the rest of all of this work. So the way I would write the third law, now this is the one you've heard of as like action reaction. This is the action reaction law. But I wouldn't, but some people say like for every action, there's an equal and opposite reaction. Like that's the law I'm talking about, but I think that is too vague of a way to say it. Like that actually gets us into a lot of trouble. So here's the way I say it. Okay. In really simple terms, there's so here, I'll read this out loud in English. It says, if there's a third law, if object A exerts a force on object B, then object B exerts a force on object A of equal magnitude and opposite direction. Okay. Now that sounds like it's a statement about how forces work. I mean, it is. But I'm saying actually it's such a strong state, it's such a specific, it's such a central statement that it's not just telling you something that's true about forces, it's really telling you what a force really is. Okay, and I know there's 4 minutes. First of all, if there, since I know I'm going to run out of, well, okay, let me write comments. Okay. With 3 minutes left, if you're trying to be totally intuitive, if ever I say force, if Newton ever says force, the thing to think is a push or a pull. That will never be wrong. A force is either a push or a pull. But okay, but what does that mean scientifically or whatever? It means a force is an interaction between two objects. Like, again, remember, in the first law and in all this Galileo analysis, what we're all about is like the whole Galileo thing is like motion is something where you study one object in relation to another object, right? And Newton's really trying to get into that one object versus two objects, like that distinction. A force is what occurs when one object interacts with a second object. A force is not something you have, it's something you do to a second object. And I know there's only 2 minutes left, but I would even you don't to write something in your notes like you don't have it, you do it. It's not like an adjective, it's like a verb. Like really. So a force is an interaction between two objects. And what he's saying in the third law is it's a symmetric interaction. It's not something that one object does any more specifically to the other one. They just do it to each other. A force is always like a tug of war or a mutual pushback, right? And really, this is another form of Galileo's principle of relativity, form number 7. It's saying once objects interact, it doesn't matter whether you look at it from the point of view of the pusher or what you think of as the pushee. That's just your point of view. If there's a push, they're both pushing on each other. If there's a pull, they're pulling on each other. It is literally like I married my wife on October 20th, 2012. I married my wife on October 20th, 2012. You want to hear something really weird? My wife married me on October 20th, 2012. Oh my God, what a, like, obviously, duh. That is not a surprise, right? Marriage is just that sort of thing. That's what a force is. It is a interaction that is symmetric between two objects. It doesn't matter how you look at it. That's enough for now. All right. So I'll see you. Oh, good. Oh, yes, exactly. Wait, okay. So I'll see you guys. Thank you very much but hang out. There's someone in the direction. Hang out for a sec. I mean, yo, thank you. I'm turning off the recording. But like person that's talking about their exam, just hang out for a second, please. Or anybody who's issue about their exam, just hang out for a second, please. But yes, goodbye. Thank you very much.
Have a good one, Professor.
Yes, have a good one. And I still owe you something, Brandon. I totally have not forgotten. I'm just behind. But yes.
No problem.
Okay, thanks. Uh, I'm